In the last video, we talked about orthogonal matrices. We gave their definition and some properties of orthogonal matrices. And in this video, we're going to talk a bit more about orthogonal matrices and explain how to characterize all 2x2 orthogonal matrices. So before we get to the 2x2 matrices, let's just ask some general questions about orthogonal matrices. For instance, is the product of two n by n orthogonal matrices also orthogonal? Well, why don't you think about this and then we'll go over the answer. All right, let's go over the answer. The answer is yes. And again, what do we have to do to check that this is in fact a correct statement? We have to take a product of two orthogonal matrices, take the transpose of that, multiply by the product, and check that you get the n by n identity matrix. So let's say that I have two n by n two n by n orthogonal matrices A and B. I want to check that A times B is orthogonal, so I need to multiply the transpose of AB by AB. Well, this is equal to B transpose AB. So if A and B are orthogonal, actually that's maybe not so. If A and B are orthogonal, then B transpose AB is equal to B transpose B, because A transpose A is the n by n identity matrix. And B transpose B is also the n by n identity matrix. So this whole thing is equal to the n by n identity matrix, which shows that A times B is orthogonal. Okay, what about the sum of two orthogonal matrices? Is the sum of two orthogonal matrices necessarily orthogonal? Again, think about it, and then we'll go over the answer. Right, the answer is no. And again, when we say no, we mean not necessarily. It may be a coincidence that the sum of two orthogonal matrices is orthogonal, but it's not always true, right? So not necessarily. And again, to justify the statement, I have to come up with two orthogonal matrices whose sum is not orthogonal, but that is pretty simple. Let's just take the 2x2 identity matrix, and I mean, you can even just take -1 times the 2x2 identity matrix. This sum is 0, 0, 0, 0. This is not an orthogonal matrix, but it's the sum of two orthogonal matrices. What about the inverse? Is the inverse of an orthogonal matrix orthogonal? Okay, take a minute and see if you can figure this one out. All right, the answer is yes. Why is this true? So suppose that Q is an orthogonal matrix, we want to check that Q inverse is orthogonal. So we need to multiply Q inverse transpose by Q inverse and check that this is equal to the identity matrix. Well, Q inverse transpose is the same as Q transpose inverse. That's a general fact about transposes. And if I have a matrix inverse times another matrix inverse, you see this pattern? I have a B inverse A inverse. That's the same as the inverse of the product AB. So using that fact, so to get from here to there, I can get, see my B in this case is Q transpose and my A is Q. So I have A, which is Q, times B, which is Q transpose inverse. And now since Q is orthogonal, Q transpose is the identity matrix, and the inverse of the identity matrix is the identity matrix. So this shows that Q inverse is orthogonal. Okay. So the inverse of any orthogonal matrix is also orthogonal. That's what we proved. What about the transpose of an orthogonal matrix? This is the last one. Is the transpose of an orthogonal matrix also orthogonal? So take a minute, pause the video, and we'll go over the answer. All right, I say that the answer is yes. And what do we have to do? We start with an orthogonal matrix. Suppose that Q is orthogonal. We want to know whether Q transpose is orthogonal. So what we have to do is we have to take this matrix that we're trying to see if it's orthogonal or not, take the transpose of that, multiply that by this matrix, and see if you get the identity matrix. Well, Q transpose transpose, what's that? I have this Q transpose transpose here. If I take the transpose of Q and then take the transpose of that, then I am left with Q. So this expression is Q transpose, which is the identity matrix. So Q transpose is orthogonal. So this is a good exercise for checking if you can apply the definition of orthogonality of a matrix, right? I mean, these are fairly straightforward proofs. Okay. I think it's a good skill to be able to do this, even if you're not learning proofs, to just be able to do the computations. You're just using the properties of orthogonal matrices. All right. By the way, if you know anything about group theory, what we showed about the product of orthogonal matrices, the identity matrix, and also the inverse of any orthogonal matrix, those are all orthogonal. That shows that the set of orthogonal matrices forms something called a group. Okay. So the set of orthogonal matrices is called the orthogonal group. Anyway, we don't need that for this, but just in case you ever learn about groups, there's something called the orthogonal group. All right, so those were some general properties of orthogonal matrices. Now let's look at 2x2 orthogonal matrices. And we'll show that all 2 by 2 orthogonal matrices have a very simple structure. And the key fact about these matrices, so right now it's just like A, B, C, D. But what do I know about these columns? These columns are orthogonal, so they form a 90-degree angle, and they're unit length. So if you look at this first vector, this first column vector, actually both vectors must lie on the unit circle because they have unit length. So here's the unit circle, radius is 1. If I draw a vector from the origin out to the point AC, this vector must be on the blue circle. And we know how to describe all the points on the unit circle. The points on the unit circle all have the form cosine theta, sine theta, where theta is between 0 and 2 pi. So what this is saying is if this angle out here is theta, then my A comma C is actually cosine theta comma sine theta. So I can write the first column of Q as cosine theta sine theta. Well, what about the second column? The second column is also of the form cosine theta sine theta. And the second, but it might be a different theta. In fact, it will be a different theta because I know that the second column has to be orthogonal to the first one. So going back to the picture, the second column must be orthogonal to the first one, the first vector. Oh, is that a 90-degree angle? Maybe it doesn't look exactly like a 90-degree angle. It's supposed to be a 90-degree angle. So what that means is that I really have two choices for my second column vector. It must be this vector or it must be this vector. Because there are only two unit vectors that are orthogonal to the first vector. So I get 90-degree angles. And how do I find these points? Well, those points are obtained by rotating the first vector either 90 degrees clockwise or 90 degrees counterclockwise. So we can actually multiply, maybe we'll use radians. This first vector, cosine theta, sine theta, as the first column, by the matrix that rotates vectors by 90 degrees counterclockwise and 90 degrees counterclockwise. So for counterclockwise, by 90 degrees, we need cosine of pi over 2, sine pi over 2, negative sine pi over 2, and cosine pi over 2. That matrix times cosine theta sine theta. And now we just need some trigonometry. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So negative sine of pi over 2 is negative 1. Cosine of pi over 2 is 0. So I take this matrix, multiply by cosine theta sine theta, and I get negative sine theta cosine theta. So the first possibility for Q is going to be negative sine theta cosine theta for the second column. The second possibility is I apply a 90 degrees clockwise rotation of my vector cosine theta sine theta. And that will give me the second point here. So this first point we found is equal to negative sine theta cosine theta. What about this remaining point? I need to take cosine. So when I rotate by 90 degrees clockwise, I make my angle negative because I'm subtracting 90 degrees. So I need cosine of negative pi over 2, sine of negative pi over 2, negative sine of negative pi over 2, and cosine of pi over 2. Well, again, that's pretty simple. Cosine of negative pi over 2 is 0. Sine of negative pi over 2 is negative 1. So negative of that is 1, and then cosine of pi over 2 is 0. So I take this matrix and then multiply it by my first column vector, cosine theta, sine theta. And what do I get? Sine theta, negative cosine theta. So this last point is, what was it? Sine theta, negative cosine theta. So Q must be either the first matrix I wrote, or it must be cosine theta, sine theta, negative cosine theta. Oh, actually, you know what? I could have just multiplied the second column by negative 1, right? To make it go the other direction. Okay, so I didn't actually have to do all this work. But, okay, we get the same thing. So these are the possibilities for the 2 by 2 orthogonal matrices. Now notice that this first matrix is just the matrix that rotates by theta degrees or theta radians counterclockwise, right? We've seen this matrix before. It's the rotation matrix. We've seen this in our discussion of linear transformations. Now this second matrix, I can write that as let's see, I think I can write that as cosine theta, sine theta, negative sine theta, cosine theta times, it's like 0, 1, negative 1, 0 or something. Is this right? No, this is not correct. Maybe it's this one? Let's see. Let's check. What am I doing? No, this is certainly not correct. I think it's 1, 0, 0, negative 1. I don't remember off the top of my head. I think it's this. Yeah. It's going to be that. And so this second possibility is the product of these two matrices. And what this product is, well, I get a matrix composition, right? I apply this first matrix here, and then I apply the second matrix. So I apply this matrix and then that matrix. Well, if you think about what this matrix on the right is doing, this is a reflection, because it keeps x the same, but it changes y to negative y. If I take this matrix and multiply it by the vector xy, I get x negative y. So you just multiply the y value by negative 1. That's a reflection about the x-axis. So I do a reflection, and then that's a rotation by theta degrees counterclockwise. And notice that these are the matrices with determinant negative 1. This this matrix has determinant 1, this rotation matrix has determinant 1, but the reflection has determinant -1. And what we just said was that these matrices have determinant 1. So now we know exactly what the 2 by 2 orthogonal matrices look like. The ones with determinant 1 are the rotations, which could be either clockwise or counterclockwise, depending on whether theta is positive or negative. And then the second one, the ones with determinant -1, those are obtained by first reflecting about the x-axis and then doing a rotation by theta degrees, counterclockwise. Okay. And again, rotation by theta degrees counterclockwise really means clockwise if theta is negative. So that gives us a description of all 2 by 2 orthogonal matrices. There's also a description of all 2 by 2, not 2 by 2, all 3 by 3 orthogonal matrices. That's a bit more complicated, and we'll talk about that in a future video.